Okay, the purpose of this video is to discuss problem number 13 out of the Sipser textbook on theory of computation. That's problem 0.13 out of chapter 0. So let's take a look at this one. Basically what we got to do is we got to show that that there has to be a clique or an anti-clique in a given graph, any graph, of at least 1/2 log 2n if the graph has n vertices. So let's first understand a couple things. First thing I want to make sure we know about is the concept of doubling, raising it to the power of 2. So if we have some number, let's say it's 1, if we double it, it's going to be 2, which is basically 2 to the 1. This here is 2 to the 0. If we double that number, it's going to be 4, which is 2 to the 2nd, and so on and so on. So basically, anytime you double the number, it's 2 to the n plus 1. Whatever the n, this is 2 to the n, this is 2 to the n plus 1. Well, the same thing works when you are halving it, taking half of something. So basically, you have 4 numbers here. You drop down to 2. That's going to be log base 2 of 2, which equals 2. You see? And so this 1 is log base 2 of 2, which equals 1. Sorry, log base 2 of 2 to the 2. Log base 2 of 2 to the 2 equals 2. Log base 2 of 2 equals 1. So basically, when you increase the number by doubling it, you're basically raising it 2 to that power. But if you reduce it by cutting it in half, you're giving it log 2, log base 2. So that's important because that comes in at the end of this proof. So now let's take a look at the next concept. The next concept is the graph, an undirected simple graph. So it's undirected simple graph. The problem doesn't necessarily state that clearly, but that's got to be in there. So there's no loops, there's no arrows and no self loops in the graph. There's no double whatever loops like that in there. It's not simple anymore. So that's the next thing. Then the next thing you have to know what a clique is. Well, if you have a clique, let's suppose we have these vertices or nodes, and we have 6 of them. A clique would be any time you have a complete graph within a graph. So let's suppose that these 3, everybody knows each other, just like in a clique with people. In a clique in a graph, all the nodes are connected to each other. So if I want to include this one in, this one would include in here. That becomes a clique. If you have a set where none of the nodes are connected, that's called an independent set. So consider this here. That's an independent set. Even though these are connected to other nodes, they're not connected to each other. So this is an anti-clique or an independent set. So once you got those concepts together, I think we're ready to tackle this proof. The next thing we have to understand is what a Ramsey number is. A Ramsey number is the minimum number, an integer, the minimum number of nodes to satisfy a couple of conditions. So we'll take the case of clique and anti-clique. The Ramsey number R of AC is the minimum number of vertices, nodes, where A is at least the size of the anti-clique is at least A, and C is at least the size of the clique. So let's suppose we say we want R of 2, 3. And we want to make a graph that's the minimum number of vertices where one of these has to be true. So let's try this. We have R of 2, 3. We just have one vertex. Can we make let's say yeah, so A is 2, C equals 3. Can we make an anticlique of 2? No, because we only have one node. This one node is an anticlique of 1. That's true. But we can't make one of 2. But that's okay, because we could do the other one. Can we make a clique of 3? No, we can't. We do have a clique of 1, but we can't make a clique of 3. So 1 isn't going to be big enough. 2 still can't do it. We can make an anticlique of 2, but we can't guarantee one or the other. And this is where it comes in. So this here is an anticlique of 2. That's true. But we can't guarantee it, because we could have a connection, and now it's no longer guaranteed. So this one has an anticlique of 1 and a clique of 2. Still doesn't satisfy the situation.